Hi again everyone. In this basic tutorial we're going to have an introduction to vector functions of one variable. Now before we get to the examples, let's motivate our study. Vector valued functions allow us more flexibility in the modelling of phenomena in 2 and 3 dimensions. For example, the orbits of planets, the path of particles, or spaceships, for example, or aircraft. Now, the most basic vector valued functions are those involving one variable. And these types of vector valued functions can be used to describe and analyse curves in space and the motion along those curves or paths. So here's an example of a vector valued function. You could also write it in the following way using I, J and K notation. Now here T is the variable, and what we would do for this particular example, T's non-negative. Think of plugging in any non-negative value of T, and for each value of T you'll get a vector that's outputted by this vector valued function R. Okay, so we're asked to consider this vector valued function for these values of t. We're asked to sketch and describe the curve associated with our function. And if a particle travels along this curve with t representing time, calculate the derivative and show that the speed of the particle is constant. And then we're asked to calculate a definite integral of our vector function. So essentially, these are just some little elements of the calculus associated with vector valued functions of one variable. Now at school, you would have seen a calculus involving functions like y equals f of x. So real valued functions of one variable. This is a generalization because it's a vector valued function of one variable. Okay, so let's go through and see if we can solve these problems. Part 1, sketch and describe the curve associated with our vector valued function. Well, you can think of any point lying on our curve having the coordinates x equals cosine t, y equals sine t, and z equals t. So let's call the curve, say, C or curly C. So x equals cosine t, y equals sine t, z equals t. Now, we're going to get some curve in three-dimensional space, so let's try to simplify the setting just for a moment. So let's forget about z equals t, or just set this t equals to 0. What will I have in the xy plane? So imagine the positive z-axis is coming out at the screen, and I'm just working in the xy plane here. Well, if we have 0 here, I get the xy plane. And what do I get with this from these set of data here? Well, I know that cos squared plus sine squared equals 1. So we have this squared plus this squared equals 1. Now, what curve is that? Well, that's just a circle with centre 0, 0 and radius 1. So here the variable t, sometimes called a parameter, would be the angle to the positive OX axis. And so as t increases, we would get this anti-clockwise rotation. So imagine the z-axis, the positive z-axis is coming out at the screen at you, and you're looking down the barrel of that axis. What you would see is this circle. So the particle would sort of just go in a loop. Now, as t increases, z must also increase, so just steadily. So what happens is we get this rotation, but the curve will be rising up above the xy plane. So our curve's rotating, but rises up above the xy plane. Steadily. So when you put these two bits of data together, what we get is what's known as a helix. So we're starting here at 1, and we're rotating and rising at the same time. So what happens is we get a sort of spring or a coil that's wrapped around the positive OZ axis. Okay, now you can think of that helix sort of being cut into a cylinder that's wrapped around the z-axis with radius 1. Okay, that's the first part of the question. Our curve is a helix, or the top half of a helix. Now, if a particle travels along this curve with t representing time, then calculate the derivative of r and show that the speed of the particle is constant. Okay, so I'm going to imagine the particle starts here, and then these little arrows kind of show the direction of the particle as time increases. Okay, well, to form a derivative, all we do is go up to each component function and differentiate with respect to t. So for part 2, we just differentiate the component functions of r to form the following. Okay, well, I want to differentiate cosine t with respect to t. I want to differentiate sine t with respect to t, differentiate t with respect to t, and then just write them as a vector. So if I differentiate cosine, I'll get negative sine. If I differentiate sine, I'll get cosine. And if I differentiate t, I'll get 1. Okay. Now we're asked to show that the speed is constant. Well, the derivative of the displacement vector is just known as the velocity vector. So what I can do now is just look at the magnitude of this vector. So let me denote this by v, and by these sort of double lines here, magnitude of this derivative. Now to calculate the magnitude, you just square each component function, add them together, and take the square root. So when I square this, I'll get sine squared t. When I square this, I'll get cosine squared t. And when I square this, I'll get 1. Now I can simplify this by using sine squared plus cosine squared equals 1. So I get root 2. So now you can see that the speed does not depend on t in this case. It's just root 2. Okay, well, let me just go back a little bit to this particular vector. Geometrically, what does it represent? Well, it's a tangent vector to our curve. So if we go back to our picture, at any point t, I can form the r dash vector, or the velocity vector, forms a tangent vector to the curve. Okay, so that's some geometric observation of what we've just calculated here. All right, on to the last part of the question. Calculate this definite integral. And this is very easy. All you do is you just integrate the component functions of our vector function. So let's see if we can do that. So we integrate component-wise. So we integrate cosine t dt, sine t dt, and t. Okay, so when I integrate cosine t, well, the areas are going to cancel each other out, so actually this first component is going to be 0. When I integrate sine t, well, you integrate and get negative cosine t, well, I'm going to get 2. And when I integrate t, I'm going to get half t squared. When I plug in these values, I'm going to get a half pi squared. Notice my answer, my answer is a vector here. Okay, not a real number, a vector. We also came up with a vector valued function here for our derivative. Okay, so it's important with these kinds of operations, you would expect to get a vector in many cases. Okay, well, let's look at the bigger picture. I've shown you differentiation and integration, but you can also define limits, and they're all defined and evaluated in a component-wise fashion. So you integrate each component function, you differentiate each component function, you take the limit of each component function. Okay, and for smooth curves, that is when the velocity vector's continuous and non-zero, r dash is just a tangent vector to the curve. Now, I've given you some examples here for you to try. Okay, so they're very similar, slightly different curve, and the answers are just down here. So have a go at this one, because the way you get good at mathematics is by doing mathematics, and see if you can solve these questions.